Oil spills such as the Exxon Valdez and the Deepwater Horizon oil spill of 2010 not only severely damaged the environment, but also cost billions of dollars to clean up. Instead of scouring the earth and using expensive techniques in an attempt to find and transport oil, one alternative is to synthesize oil by converting microalgae into crude bio-oil. Bio-oil derived from algae is considered a greener alternative to traditional fossil fuels because the CO2 produced by burning the fuel is consumed by growing algae, which are then converted into more bio-oil. This creates a contained cycle that greatly reduces the negative impact burning fuel has on the environment.
Hi, my name is Chris Fair. I'm an undergraduate studying chemical engineering at the University of Michigan. This past summer I was a participant in the SHARE program, which stands for Summer Undergraduate Research in Engineering. I was under the advisement of Professor Phil Savage, whose work focuses on converting microalgae like this into biofuels.
To do this, we treat the microalgae with a process known as hydrothermal liquefaction, in which it is exposed to high temperatures and pressures. This converts the microalgae into a biocrude oil, which can then be upgraded into better and more usable forms. This past summer, my research focused on the upgrading of biocrude oil through the use of different kinds of catalysts, mainly platinum on activated carbon and molybdenum carbide. And more specifically, my project focused on helping to develop a kinetic model for the deoxygenation of oak creosote. Where this fits into the upgrading process of the biocrude oil is that the biocrude tends to contain heteroatoms such as oxygen and nitrogen. And so if we could find a way to remove these atoms, it would greatly improve the quality of the oil. So by creating a kinetic model and a reaction network for removing the oxygen from oak creosote, we could try and relate that to removing oxygen atoms from the biocrude oil. I worked with two different starting reagents this past summer. One of them was oak creosote, which was used exclusively with the platinum on carbon catalyst, and the other was palmitic acid, which was used with the molybdenum carbide catalyst. I also worked with two different kinds of batch reactors, which can be seen here, the main difference being that the second one had an attached pressure valve which allowed us to remove all of the oxygen from the reactors before pressurizing them with either helium or hydrogen. Now that you know a little bit about the process and the purpose of my research, let me take you through how it's actually done. First, the reactors are loaded with the desired starting reactant, which in this case was palmitic acid. Then the catalyst is weighed out and added to the reactor, followed by the desired amount of deionized water. After loading the reactors, they are tightened shut and flushed with helium to remove any oxygen that may be present, and then they are pressurized with either helium or hydrogen. The reactors are then loaded into a fluidized sand bath, the temperature of which varied from experiment to experiment, but it was typically between 300 and 400 degrees Celsius. This is hot enough to melt lead. This temperature also brings the pressure inside the reaction vessels up to about 3000 psi, which is the equivalent of 1 Honda Civic per square inch. After the reaction is completed, the reactors are removed from the sand bath and quenched to room temperature. The gas inside the reactor is then analyzed prior to extracting the liquid products and the catalyst into centrifuge tubes. These tubes are then centrifuged to separate the liquid products and the catalyst. Finally, samples of both are taken to be analyzed. In the future, we plan to continue analyzing our results and complete our kinetic model, as well as further investigating the efficacy of other catalysts. We hope that by completing this model, it will give us better understanding of how to improve this biocrude, and this would in turn allow us to upgrade these biofuels using less energy and in a more economical fashion, thus making biocrude derived from microalgae a more viable source of alternative energy.